the product of the thermite reactions. It's sputtering around like the thermite on the French car, and afterward you collect the dust. This is commercial thermite. You can buy this on the web, play with it.
Isn't that gas aluminium oxide?
So this is the dust from the commercial thermite collected, and this is the dust from the World Trade Center, and it contains exactly the same iron spheres. And now I have to bother you with a little bit of technology, because what we are doing is something called energy dispersal spectroscopy. In short, we hit such a particle with an electron beam, and this can be done with an accuracy of down to 100 nanometers, which is 1/10,000th of a millimeter. We can hit one spot here with an electric beam, and there comes a signal back in form of X-rays, and these you can analyze. And this is such an analysis of the X-ray response from this method. And from the different peaks here, the different frequencies, you get information exactly which elements are on the spot you hit with the electron beam. And the lesson to learn here is you have the same ingredients in the iron spheres from the commercial thermite and from the WTC dust. This is Fe means iron, Ca means calcium, Si means silicon, Al is aluminum. There's another iron line here. You see the same elements here from the commercial thermite. With one single exception, if you may notice, there's a little S here is for sulfur, and the calcium peak here is a little bigger than over here. This is a contamination of calcium sulfate, which is the chemical name for gypsum, plaster of Paris, which is used for waterboards. So this is because the whole center of the towers, I don't know about 7, but the towers, the center, the core, was embedded in waterboard, which is a brilliant isolator for fires, gypsum. And this is contamination from there, you see. Okay? Now, Jones asked himself also the question, when you use an explosive or an incendiary, there's always something left. The process does never run to completion. So maybe there would be a chance to discover unreacted thermite in the dust. And yet the answer was yes. Among others from the sample from genetic pink. Here you see such a remain from a thermite reaction. But this is not the same kind of thermite which was used on the French car. This is, we call it nano-thermite, because it's been prepared by nanotechnology. It's a basically, fundamentally different way of producing materials than usual. If you have to make a finely divided powder, what you usually do is you take something bigger and grind it, okay? So you make something bigger, smaller. In nanotechnology, you start from this bottom-up approach. You start from the atom, so you build the material from the atom upwards. This has two very important consequences. One thing is that everything gets smaller. We are operating on a scale of length here. 1 nanometer is 1/millionth of a millimeter. It's very small. And so this is the scale you're operating. It's a little bigger than atomics and molecules, but it is beyond molecules. And the other thing is that in this procedure, you have the option of adding other substances to the material. So, and because everything gets smaller, it reacts faster and more efficiently, and because you have the option of putting in other stuff, you can use the energy of the thermite for actually converting it into an explosive. We do not know, I must emphasize this, I know this presentation has been announced, we're using the term explosive thermite. We do not know actually what this thermite served as exactly. Let me give you a few more details. This is an electronic microscope picture on the same sheet, and there are no pictures on the electron microscope spectroscopy. So this is the red layer you have here, down here at the bottom, and the gray layer you have on top. I show you this for giving the proportions of these chips. This is 1/10 of a millimeter. So these are very thin, and usually the length of the chips are the same order of magnitude. The first one I showed you was a real big one, real big fat one, several millimeters. Usually they're much less. So you actually need a microscope to find them, and also have some skill and experience in finding them, particularly those which can do what I'm going to show you now here, because they can react, and in the reaction they produce iron. This is the predominant property of the red-gray chips that we have discovered, is that they are reactive and they produce iron in the process. This is a semi-reactive chip from the dust. With some luck you can find them. And the point is here that the iron sphere is connected to the chip. It's a semi-reactive. This is a chip which has been burned in the laboratory, and you see the iron sphere being formed here. And I believe you, I'm not going to bother you with more energy dispersive spectroscopy. But what we can do is we can analyze exactly the composition of these spheres being formed from the reactive nano-thermite chips, and these are iron spheres. There's also some aluminum and silicon in, which there should be, as you saw before from the commercial thermite, but it's predominantly iron. Point is, number one, the nano-thermite, the nano chips, the red-gray chips, produce iron in reaction. This is our main argument for identifying this as something which shouldn't be there. We don't know what it is. This has led to a scientific publication where I have the honor to be on the team together with 8 other distinguished scientists, one of them sitting here in the bandstand, Dr. Frank Legge from Perth, and this came out on April 3rd last year, and in the meantime it has not been shut down, and it has not been challenged by any serious scientific means, and this makes me quite confident. It must be the most reviewed and thoroughly studied paper in recent history, and I'm very confident now. If it has really stood this year without any serious challenge. And so we still believe in our conclusions. We have found something in the dust which can do things. Being an incendiary or being an explosive, we're not sure. I'm going to show you in a while. I have a guess. We should just say there's something there. We shouldn't be there. And those who put it there should tell us how they made it and how they got it there. Now, so my final thing would be some guess. I'll close with another video from David Chandler. This is the South Tower exploding. And if somebody has thinking about all these squibs coming out of the towers, if they could be pancaking of the building, well, you're going to see here 3 things. First, you'll see explosions, actually these squibs, coming out of the South Tower above the impact point of the airliner. Next, you'll see that the top of the building disappears as it tumbles over it. Remember that the South Tower started to tilt, and it should have continued tilting, because this is what things do, but it doesn't, it disappears. Most importantly, you'll see rocket fragments. These are fragments which, for once, move to the ground faster than free fall. And it's easily comparable because you have the debris falling freely just beneath it. But it's actually racing to the ground faster than free fall. How can anything do that, move faster than free fall? Only if you have a rocket tied to your back and you're moving downwards. Or another fragment which is coming out and then suddenly change direction 90 degrees. How come? If you throw a stone, it will continue in a trajectory which is parabola, but it will go like that. But here you see something coming out and then suddenly it changes 90 degrees, makes a 90-degree turn. This could be our thermite. I think this could be our thermite. That's all I say. It's not so long. I'm finishing it very shortly.
This particular video clip is rich in details that call the official story into question. Notice the numerous explosions on the west side of the building above the impact point. As the top 30 floor section falls, it tips to